Hello everybody, my name is Karim and I'll be doing a final exam review. I'll be going over the reviews that are in the workbook. I'll be going over exam 1, exam 3, and exam 4. I won't be doing exam 2 as I already have a review for that, a review video. So let's go ahead and get started. I apologize for the marks here. It's taking me multiple tries to get this video right without me stuttering so much. But anyways, let me fix it. Okay. So in exam 1 for module 1, the first question asks for us to give the correct chemical formulas, including charges when necessary for the following. Okay, so for A, it's iron 3 nitrate. So remember, for transition metals, this number is basically the charge, right? So it'll be Fe3+, right? And then remember nitrates, nitrites, and hyponitrites, you have to remember your rule of 7, okay? Remember that 8 is for the baseline, the reference number for oxygens. So we have Fe3+, nitrate will be NO3 minus 1, right? And all of this comes from the rule of 7. So this is treated as an ionic bond because of the ions here. So remember, for ionic bonds, the charges basically become subscripts. So this -1 will go to iron subscript and this +3 will go to nitrate's subscript. So because we have a 1 as a subscript, we don't really have to include it. So our formula would be Fe. It'll be a 1 here, but if there's no number there, it's a assumed 1. So it's Fe parentheses NO3 nitrate and then the charge of iron. Okay. So then next one is very similar, except we have nitrate. So remember, nitrate 8 is your reference number, where nitrate is positioned in the periodic table. The reference number would be 3 oxygens. You go down an oxygen and it becomes ite. So nitrite would be NO2 minus 1. Remember that the change in oxygens doesn't change the charge. So then we have nitrite and then aluminum. Aluminum is Al and it has a charge of +3. Okay, so like A, we just put it all together. So it'll be Al, it'll be a 1, right, as a subscript, but it's already assumed. So it'll be Al parentheses NO2 3. Okay, the reason that we put the parentheses is because we already have a subscript here for the oxygen. So we don't want to get it confused with this subscript which is the charge of aluminum. Okay, so then for the next one we have calcium phosphate, again ionic. So calcium in the periodic table is in group 2, so it has a +2 charge. And phosphate, well, you have to look at your rule of 7, right? Where phosphate is positioned, the reference number of oxygens is 4. So phosphate is PO4 and it has a charge of -3. Okay, now we put it all together. We notice that for the charges, we don't have a 1 anywhere, so we have to assume all the numbers. So Ca, right, the charge of phosphate will go to calcium, and then calcium's charge will go to phosphate's subscript, so it'll be PO4. We were going to put a parenthesis so we didn't get confused with oxygen's 4 and calcium's charge. Okay, that's pretty much it. And then hypochlorite, that's not necessarily a bond, it's just to see if you know your rule of 7. Remember, it goes 8, ite, and hypo, ite. So 8 as a suffix is for the reference number, Ite is for one less than the reference, and then hypo as a prefix will be two less than the reference number. So we're dealing with chlorite. Chlorate would be ClO3, right? That's our reference. So chlorite would be ClO2. Hypochlorite will be just ClO. Okay, so that's our answer. Okay. Same thing with the next one. The charge on the chemical species iodate is, again, this is just testing your rule of 7. If we look at the periodic table where iodine is at, the rule of 7 will tell us that's -1, just because it's in the halides group. Okay, now we look at 3. The number of molecules represented by 35 grams of carbon dioxide is approximately. So this is just conversions. So remember, you go to grams to moles to molecules, and then finally to protons. Molecules could also be atoms. The way you go to from grams to moles is just dividing by the molar mass. Moles to molecules is just multiplying by Avogadro's, which is 6.022 times 10 to the 23. Remember, it's not -23 because it's a huge number of molecules. So then molecules to protons is just multiplying by the atomic number. Just atomic number. Okay. So here we're given grams, and we want to go from grams to molecules. So then basically what we have to do is just find the molar mass of carbon dioxide. Remember that carbon dioxide is CO2. So carbon has a molecular weight of 12.01, and then oxygen has a molecular weight of 16, but we multiply that by 2 because we have 2 oxygens. Okay, so then here we get 32, and then here it's just 12.01 because we have only 1 carbon. So we add those up, we get 44.01. So then all we do, right, it's 35 grams of carbon dioxide. So we want 1 mole of carbon dioxide. So then we divide by the molar mass, 0.01, just grams per mole, Okay, so this would give us our moles of carbon dioxide. And then we want to find out how many molecules we have of carbon dioxide entirely. So we only have 1 carbon dioxide, so we're just going to multiply by Avogadro's number once. Molecules, and then this represents how many molecules are in a mole. Okay, so if we do that calculation, let me do it real quick. It's 35 divided by 44.01 times Avogadro's. So we should get around 4. We could just say 8 times 10 to the 23rd. That's our answer. Okay. So for number 4, we have determined the number of moles of chlorine atoms in calcium chloride. So whenever we're given a molecule, it's best to just write out its formula rather than have the name. So calcium, so we have Ca2+, right? And then chlorite, it's ClO2 minus. So then calcium chloride will be CaClO2, 2. Okay, so this is tricky, right? Because we have grams and we want to go to moles. the way the problem is worded makes you think that you have to go to atoms, right? But that's not what the question is asking. It's just asking for the number of moles, okay? So don't get confused. Whenever it says determine the number of moles of chlorine atoms, you're basically just finding the moles of chlorine, okay? It is worded really weird, but you're finding the moles of chlorine, okay? So again, we're given grams of CaClO2, 2, and then we want to go to moles. Like up here, we want to go from grams to moles, and then moles to, well, we just want to stop at moles, right? Because that's what the question is asking. Okay. So then 1 mole, and all we do is just find the molar mass, right? I already have the molar mass here somewhere. If not, we could just calculate it real quick. Yeah, we'll just go ahead and calculate it. So we have, I should do it here. Okay, so we have 1 calcium, right? And then we have chlorine and oxygen. And then for each of these, we'd have 2 times the amount because they're being multiplied by 2, by the charge of calcium, right? So calcium's weight is 40.08. Chlorine's weight is 35.45, but we're gonna have to multiply that by 2, and then oxygen's weight is 16. Okay, but we're gonna have to multiply that by 4 because we have 2 oxygens, but remember that they're being multiplied by 2 because of this charge right here. Okay, so we can just calculate it real quick. I just like to do these multiplications separately and then just add them up at the end. So we have 16 times 4, which is 64. And then we have 35.45 times 2, which is 70.9. And then, well, we just have calcium. So it'll be 70.9 plus 40.08 plus 64. So it's 174.98. So we'll go ahead and put that here. Okay. So remember, at this point, we're just gonna get moles, right? We don't wanna go to atoms because it's just asking for moles. So right here, we should theoretically stop, okay? But remember, it's asking for chlorine specifically. So now we have to look at our formula and see how many chlorines we have. So remember, we have 2 chlorines, okay, because of this charge right here. So we have 2 chlorines. So then we'll just multiply all of this by 2. Okay, so then it'll be 83 divided by 174.98, and that'll give us the moles of calcium chloride, but then we'll have to multiply it by 2 because of how many chlorines we have. So we'll get 0.95 moles. Cool. Okay, so number 5 says calculate the mass of lithium perchlorate that needs to be dissolved in lithium perchlorate aqueous solution to contain 2.5 times 10 to the 23 atoms of lithium in the solution. Okay, so remember that we want to start off with the formula. So lithium perchlorate, lithium has a charge of +1. Yes, okay, and then perchlorate, so again, it's the rule of 7, so that it will be ClO4 minus 1. Okay. So then if we put them all together, it'll just be LiClO4. Okay. So the question is really weird, right? But basically all we have to do is just work backwards from these little steps over here, right? So we're given atoms. We're given atoms in the question, right? Okay. So from atoms, we want to go to grams because it's asking for the mass. So we want the mass in grams. So basically what we have to do is just the opposite of these operations here. So from grams to moles, we divide it by the molar mass. From moles to grams, we'll just have to multiply. And then from moles to molecules, we multiplied by Avogadro's number. In this case, we're going to go backwards. So going from atoms to moles, we'll just divide. Okay? Okay. So we have 2.5 times 10 to the 23rd atoms, right? We want to cancel out atoms, right? And we want to get moles out of this. So in 1 mole, there's 6.022 times 10 to the 23 atoms in 1 mole, right? Okay. So yes, we divide by Avogadro's, and that'll get us 2 moles. And then the final step is to go to grams, right? And we're gonna divide by 1 lithium. Okay. So then we have to divide it by the molar mass. So we're gonna have to go ahead and find it. So we have 1 lithium, 1 chlorine, and 4 oxygens. Okay. So lithium has a mass of 6.94. Chlorine has a mass of 35.45. Then oxygen has a mass of 16, but we have 4 of them. Okay, so 16 times 4, we already did this, it's 64. So now we just add all of these. So it'll be 6.94 plus 35.45 plus 64, which will give me a total mass of 106.39. And we'll go ahead and put this down here. Yeah. Okay, grams per mole. Hey everybody, sorry, just quick correction. I did mess up here. It wasn't supposed to be divided by molar mass. Instead, it should be multiplied, right? So before I did get 4 times 10 to the negative 3, which is pretty small, but with the correction, it's 44.2 grams, right? So do remember to get to atoms, from atoms to moles, you divide by Avogadro's, right? And that'll give you moles, and then moles to grams would be multiplying by molar mass. Okay, so please remember that. I apologize on my part. Okay. So to the next question. Okay, so now we're in module 2, right? So 6 says the hybridization of the central atom and the geometry of the carbonate ion are, okay, so this is basically a Lewis structure problem, right? So carbonate, remember the formula is CO3 minus 2, right? That's our formula for carbonate. So if we want to draw the Lewis structure, there's different ways that you can do it. The way that I like to do it is I like to count up all the valence electrons. So oxygen has 6. We have 6 oxygen, so that's 18 valence electrons for oxygen. Carbon has 4, so that'll be 22, right? So with carbon and oxygen, we have 22 valence electrons, right? But then we have to take into consideration the charge. Because electrons are negative, a negative charge will just add on to it. So would have 24 valence electrons. Okay. We know that our central atom would be carbon because it's the least electronegative, and also it's the odd one out. So that's a good rule of thumb. So carbon would be our central atom, and then we have 3 oxygens surrounding it. And we know for sure that there's going to be a bond between carbon and oxygen. We don't know if there's going to be double bonds or triple bonds yet, but we know that at least we have a single bond between carbon and oxygen. Okay, so then now we just dump in all the 24 electrons, right? We do all the outside atoms first, and then whatever we have left over, we just fill it in on the inside. So then 24 electrons here, we have 1, 2, 3, we have 6 electrons, right? Remember that each bond counts for 2. So we have 6 electrons total. We would need 12 dashes, right? Remember that each dash represents 2 electrons. So right now we have 1, 2, 3. We're gonna need 21 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so that's all our valence electrons. We don't have anything for the central atom, right? So we could keep going here. We could get the right structure, which I do encourage, sure. But we already have our answer here. Even if we get double bonds or triple bonds between the carbon and the oxygen, it's going to stay the same hybridization. So we can already find the hybridization here, and since we already laid out all our valence electrons, we can see that carbon doesn't have any lone pairs. So we could just find our hybridization here. So it'll be S, SP, SP2. Okay, so we can already rule out all our SP3s, SP3Ds, and SPs. Okay, we don't know if it's none of the above. So we have B and F. For our geometry now, we have to look at how many electron regions we have. Again, sure, we could finish out the Lewis structure, but we already have all the electron regions that we need. So we have 1, 2, 3. 3 electron regions without any lone pairs give us trigonal planar. So that should be F. And just for education purposes, right, I'll just finish out this Lewis structure. So after we laid out all our electrons, we can simply just go with the octet rule. Remember that CNOF or Func are our elements that have to follow the octet rule. Okay, meaning that they have to have 8 electrons around them at all times. So we have 1, 2, 3, 4, 5, 6, 7, 8. So that's true for all the oxygens, but then carbon, 1, 2, 3, 4, 5, 6. Carbon has 6, right? So in order for carbon to obey the octet rule, one of the oxygens has to make a pair, a bond, right? So now it's 1, 2, 3, 4, 5. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now carbon and oxygen fulfill the octet rule. Okay. The last step is formal charge. Okay. Remember that for the best Lewis structures, we want a formal charge of 0 at the central atom if possible. Okay. Without breaking the octet rule. So the formula that I use for formal charge is 1 minus has. 1 meaning the valence electrons for that specific atom from the periodic table, and has is the valence electrons that are on the actual structure, right? So for example, let's do carbon, right? Carbon wants 4 valence electrons from the periodic table, right? And it has, so for formal charge, remember that you break bonds in half. and you only count them as singles. So 1, 2, 3, 4. 4. It has 4. So it'll give you a formal charge of 0 at carbon. So that's good, right? Because we want a formal charge of 0 at the central atom every time, if possible, right? Remember that octet rule kind of has a, how would I say, like a hierarchy to the formal charge. But okay, so we know that carbon is 0. Okay, now let's look at these oxygens. Oxygens want 6. Let's see how many they have. 1, 2, 3, 4, 5, 6, 7. Okay, so that's -1 for this one. And then this one looks the same, so it'll also be -1. Okay, this oxygen, 1, 2, 3, 4, 5, 6. So it wants 6, it has 6, so then it'll be 0, right? So then this would have a formal charge of 0. Okay, so now let's see if it makes sense. Remember that we're talking about carbonate. Carbonate has a -2. So we want to see if overall the formal charge adds up. So octet rule is followed. Formal charge also is obeyed, right? Because we have 2 negatives. Negative plus a negative is a negative. So then it's a -2 charge. So then this is our structure. All right, cool. 7. The number of resonance structures for the nitrate ion satisfy the octet rule is, okay. So all we have to do is just draw the structure and then see how many resonance structures are possible. So nitrate is NO3 minus, okay. Let's count up the valence. Right now it's kind of tedious because I'm explaining it, but with practice, you do get better. Okay, so that's what, 23? Yes, sorry, I can't do math without a calculator anymore. Okay, and remember the -1 charge, electrons are negative, so negative charge will add up. So overall we have 24 electrons to give away. Okay, so nitrogen would be our central. Remember, it is going to be surrounded by the 3 hydrogens. We know that there's going to be a bond between the nitrogen and oxygen. Sorry, did I say hydrogens? Oxygens, sorry. It's going to be surrounded by 3 oxygens. There is going to be a bond between the nitrogen and oxygen, but we don't know if there's going to be a double bond or a triple bond. Okay, now we lay out our electrons. We have 24, so we need 12 dashes in total. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that's fine. Okay, octet rule, remember CNOF. Oxygen follows it. Nitrogen doesn't follow it yet. So we're gonna take away 1 valence, not valence, but lone pairs from the oxygen, and we're gonna make a double bond for the nitrogen. Okay. So now the octet rule is followed for all of them. Okay, now let's see formal charge. Let's see. Okay, so we know that this one's going to be -1, this one's going to be -1, this one's going to be 0, right? There's almost a pattern with oxygens most of the time. So nitrogen, we want 5. So we want 5, right, from the periodic table. Let's see the formal charge. 1, 2, 3, 4. So it's a -1 on the nitrogen. So this is the exception that I was talking about, right? So yes, most of the time we do want a formal charge of 0 at the central atom for nitrogen, well, for any central atom, right? We want that. But sometimes the octet rule takes priority, and we obey the octet rule instead. So this is one of the cases, because if we were to add another bond right here, then the octet rule would be broken for nitrogen and oxygen. Well, not oxygen, but just nitrogen, right? So then this is our structure. Okay, we see that we only have a single bond. I mean, one single double bond. That's kind of confusing. So remember, for resonance structures, that means it's the possible ways that this ion can exist, right? We don't necessarily just have to have a double bond at the leftmost oxygen, right? This can exist as a double bond here or here. So the number of resonance structures is 3, right? Because we have 3 possible spaces for the double bond to live in. So it'll be 3. Okay. Okay, let's do 8. Draw the best Lewis structure for bromate ion, showing all atoms, lone pairs, resonance forms. Okay, that's fine. Bromate. Okay, so we have to remember our rule of 7. So bromate is going to be BrO3, right? The 8 reference number. And then we know it's going to be a -1 charge because it's in the highlight, right? Okay, like always, it's kind of valence electrons. So we have 18 for oxygen, and then bromine we have 7, and then we're gonna add 1 more because of this negative charge here. And I can't do simple math in my head. Okay, 26. Okay, so now bromine is going to be our central atom, right? Because it's the low one out. I know I said that the most electronegative, or the least electronegative, would be in the middle. Well, I guess that's true. Yeah, it's farther out than oxygen. Sorry. Okay, yes. So bromine would be in the middle. It's going to be surrounded by 3 oxygens. Okay, then we need 26, so we have to lay out 13 little dashes, right? Okay, so we have 3 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then the final 2 are gonna go to bromine. Okay. All right. Octet rule, all of them are following the octet rule, right? And then we want a formal charge of 0 at the central atom. So let's check bromine first. Bromine wants 7, and then it'll be 1, 2, 3, 4, 5. So we have a +2 in the middle. Okay, so now we want to bring this to 0, right? Because bromine can have more than 8 electrons because it doesn't have to follow the octet rule. Okay, so what we could do, right, a simple fix would just be drawing those 2 dashes, right, and taking away, sorry, this is not a good eraser, but taking away a lone pair from the oxygens and then just putting it as a bond to the bromine. In this case, we're not breaking the octet rule for the oxygens, and bromine can have more than 8 electrons. Okay, so now we can check again. Bromine wants 7. 1, 2, 3, 4, 5, 6, 7, and we have 7. Okay, so now we have a formal charge of 0 at the central atom. Let's check these other ones. We have 0 here, and then 0 here, and then we have -1 here. Yes, so we have a -1 charge for one of the oxygens, which matches up with our overall charge of the structure, of the compound, sorry. Okay, now we did all atoms, we did all lone pairs, now we need resonance structures. Okay, so what we could do is simply see all the possible combinations that we could have, right? So right now this is one combination, but remember, it's all the possible ways that bromate can exist. So we can have a combination that's like this, right? Where we can have the double bonds on each side, or we can have kind of like an inverse of what we have now, right? So it's like this. So it's just seeing the possible combinations that we could have without repeating each other. And I think it's just 3, right? Because we can move this double bond here, and then have a single bond here, but then also we could have a double bond here and then a single bond over here. So yeah, I think it's just 3. All right. So we could do this. Now remember, whenever you're doing resonance structures, you have to put the double arrow to signify it could be this or this. And then we could do whoops. -1. Yes, so then that'll be all our resonance forms. Okay, let's do 9. How many bonds and how many lone pairs does an oxygen atom and a carbon atom must have to have a formal charge of -1? Assume the oxygen rule is obeyed. Okay, so we're talking about formal charge. So basically we just follow ones minus has. So we have oxygen and we have carbon. All right, so we want a formal charge of -1. For oxygen, I mean, we've already seen it, right? A -1 charge for oxygen would be this: a double bond and 2. No, just kidding. Sorry, that's a 0 formal charge. Oxygen, a -1 formal charge would be this, right? Because oxygen 1, 6. We have 1, 2, 3, 4, 5, 6, 7. So that'll be a -1. So we would need 3 lone pairs and 1 bond. How many lone pairs? How many bonds? Okay, yes. So let's just scratch off the ones that don't make sense. So no, we don't need 2 bonds. No, 3 bonds. No, we don't need 3 bonds. So that one's right for oxygen. Now let's check carbon. Carbon, remember, wants 4. So it has to have 5 around it. Okay. Now since it has to follow the octet rule, we could just put 8 around it and then check the former charge. The former charge here. So then it'll be 1, 2, 3, 4, 5, 6, 7. So then here it's 4 minus 7, which would be -3. Don't quote me. This is -1. Yes, okay, it would be -3. Okay, so we have to bring this down. What we could do is just add another bond, right? Because remember, these can be cut in half. Well, for formal charge, they have to be cut in half so they can count as 1. Okay, so that it's easier, well, not easier to work with. How would I explain it? It's not easier to work with, right? But for formal charge, right, you do need to cut these in half, and then they'll give you single values. So here we have 1, 2, 3, 4, 5, 6. So now it's 4 minus 6, so now it's -2. So then we can add another bond here. Now we have 1, 2, 3, 4, 5, which is what we want, right? -1. So for carbon, yes, it's 3 bonds and 1 lone pair, which is kind of like the inverse of oxygen, which is fun, I guess. Okay. All right. So then 10 is just asking for the Lewis structures. You could memorize them, but I don't suggest that. I don't think that's a good way of doing it. Yes, it's kind of tedious to go about it this way, but that's basically how it has to be. So ammonium, remember it's NH4 plus. You do have to know your formulas. Ammonium is kind of something that you're supposed to know. Also ammonia, acetate, acetic acid, and acetone. Okay. So count up valence. So we have 4 from the hydrogen, we have 5 from the nitrogen, and then so that'll give us 9. But now we have a plus. Remember, electrons are negative, so if we add a positive, it will give us a lower value. So it'll be -1. So then we'll have 8 valence electrons total. Okay. Nitrogen is going to be in the middle because it's the odd one out. The 4 hydrogens are going to go around it. Okay. And we know that for sure there's going to be at least a single bond. Okay. So now let's lay out our electrons. We need 4 dashes, right? But we already have them. Okay. And then we're gonna check for octet rule, CNOF. Nitrogen has to follow it, and it is following it. Okay, cool. Now form a charge. Hydrogen wants 1, and it has 1. So that'll be 0. So that's 0 for all the hydrogens. And then the former charge of nitrogen would have to be our plus value, right? Because hydrogen wants 5. Nitrogen wants 5, and it has 4 around it. So it's a +1 charge on the nitrogen. So this is our best lowest structure. Okay. Carbon dioxide, it's CO2. So we will have 12 valence from oxygen and 4 from carbon. That'll be 16. Carbon is going to be in the middle, least electronegative, and then it's going to be surrounded by 2 oxygens. We know that at least there's going to be a single bond between them. Okay, lay out our 16 electrons, so we need 8 dashes in total. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. Now former charge, or octet rule, sorry. So the oxygens are following the octet rule, but not the carbon, right? So what we could do is just add more dashes from each. Okay. And you'll see why I did from each in a minute. Okay, now we check for former charge. Carbon wants 4, it has 4, it's 0. And then oxygen wants 6, 1, 2, 3, 4, 5, 6, and it has 6 for both of them, right? So we have a 0 charge for all of them, which is what we want because carbon dioxide doesn't have a charge. So the reason that I took from both of these oxygens is because if I took from just one of them, right, I would get a positive charge for this oxygen, and we can't have charges, right? We want the lowest number for former charge, right? The least amount of elements to be 0. Okay. All right. Okay. Sulfur hexafluoride. So sulfur hexafluoride, that means 6 hex. What's supposed to be is 6 fluorides. Okay. So we know. Okay, let's count valence then. So then it'll be 6 times 7, right? Which is 42. Yes, because, okay. So it's 7 because of the valence electrons for fluorine. We have 6 of them, so 6 times 7 is 42. And then sulfur will have 6. So this will be 48. It doesn't have a charge. Okay. So then sulfur will be in the middle, and then it will be surrounded by 6 fluorines, right? Now, we know that for sure there's going to be at least a single bond. We don't know about double bonds yet. Yeah, that's 6. Cool beans. Cool beans. Okay. All right. So that's all of them laid out. Okay, so we know that this is the general structure, right? Okay, now let's lay out our electrons. So we have 48 electrons to give away, so we need to lay out 24 dashes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. We check for octet rule, right? All the fluorines are following it. You know, fluorine is part of CNOF, so we're good there. And then sulfur wants, okay, so we're good on the octet rule. Now let's check formal charge. So we want a formal charge of 0, right, for the best structures. Sulfur wants 6, and it has 6 around it. Okay. And then fluorine wants 7, and it has 7 around it, right? 1, 2, 3, 4, 5, 6, 7. So this is the best structure, right? With each fluorine having 3 lone pairs and 1 bond, and sulfur having all the 6 bonds. Okay, I apologize. It was getting a little dark in my room. Okay, well, let's get into module 3. All right, so question 11 says the carbonyl group is present in all the following organic functional groups except, okay, so all we have to do is just remember our functional groups. What it means by carbonyl is just a carbon double bonded to an oxygen, right? That's all it means. That's all a carbonyl is. Okay, so, need more light, yeah, I hope that's good. Okay. So basically we just have to look for this, right? So remember cake, it's double E, cake, double A, sorry. Okay, so it's cake, right? Cake is all of the functional groups that have a carbonyl, right? So C is for carboxylic acid, carboxylic, oh, I think I misspelled that, acid, okay? And then this ester is supposed to go here, but I mean, it's cake, right? But yes, this E is an ester, this K is a ketone, this A is an aldehyde, and then this other A is an amide. Okay, so we have carboxylic acid, aldehyde, amide, ketone, and ester. These are all containing a carbonyl group, so all we have to do is just look for the one that doesn't, right? And it's ethers. Ethers does not contain a carbonyl group. Okay. Now let's do 12. A student is asked to name an organic structure and identifies the structure to be 4,5-diethylhexane. The correct name for this organic structure is, okay, so all we have to do is just draw this and then name it correctly. 4,5-diethylhexane. To draw organic structures, first we have to see how long the carbon chain is. So this hex will tell us that it's 6 carbons long, and this ane will tell us that it's an alkane, so it only contains single bonds. Okay, so it's just a single bond chain. So it'll be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, yes. So it's a hex, right? Because it has 6 carbons. And it's an ane because it's a, what's it called? It all has single bonds. It's all single bonds, okay? And then diethyl. ethyl, remember that it's 2 carbons. It's a 2 carbon functional group, or substituent, sorry, it's a 2 carbon substituent. And this di tells us that we have 2 of them, okay? And these tell us where the ethyls are going to be. So on the 4th carbon and the 5th carbon. So 1, 2, 3, 4, we have an ethyl, and then 5, we have another ethyl. So all we have to do now is just correctly name it, right? So we're looking for the longest chain and the least and the shortest way to our substituents, right? Once we do find them. So let's see, 1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay, so it seems, let me see, 1, 2, 3, 4, 5, 6. Yes, so it seems that our longest way would be from here all the way to here, right? Remember that we always want to identify the longest carbon chain. So it's 1, 2, 3, 4, 5, 6, 7. So now we have a 7 carbon chain, which is what we want, right? So instead of a hexane, it'll be a heptane. Okay. So now we can go here and just cross out all the hexanes, okay? Heptane, okay? Now we identify our substituents, and then we want to number them in the shortest way possible. So here we have a methyl, and here we have an ethyl. So we would start numbering from this end rather than this end because it takes more carbons to get to the substituents than this side. Okay, this is the shortest way. So it'll be 1, 2, 3. So we have a methyl on the 3rd carbon and then an ethyl on the 4th carbon, right? Because that's the shortest way to get there. Okay, so it's 1, 2, 3, 3 methyl, 4 ethyl, right? And we always want to name these alphabetically. So ethyl will come before methyl. So it'll be 4 ethyl, 3 methyl. Oh, yeah, I always do this, sorry. I always do this. I always cram them in because I'm trying to be more efficient. 3 methyl. Yes, heptane. Okay. Okay. So you see, the numbers didn't necessarily matter. It mattered that it was in alphabetical order, right? Ethyl came before methyl. And then heptane will always be at the end because it identifies our longest carbon chain. Okay, so then it should be A. All right. 13, what is the correct name for this structure? So same thing, we're just gonna use our naming method. So we want the longest carbon chain and the shortest way to our substituents. So let's see. Let's start from here. 1, 2, 3, 4, 5, 6. Okay. Sure. Let's start from here. 1, 2, 3, 4, 5. No, that's not long. 1, 2, 3, 4. No, that's not long either. So let's see. So I believe that our longest chain is going to be 6. Let's see here. 1, 2, 3, 4, 5, 6. Yeah. So it'll be, this is our longest chain. 1, 2, 3, 4, 5, 6. So we know it's a hex, we know it's an ane, an alkane, right? Because it's all single bonds. Okay, now we have substituents, right? So we have 2 methyls. So because we have the same substituents, we could just say dimethyl. And before the dimethyl, we can put where they're found at. So let's see what's the shortest way. So 1, 2, so this is on the 2nd carbon. 1, 2, 3, 3rd carbon, 4, 5, 6. Okay, now let's do it from here. 1, 2, 3, 4. This is fourth carbon. 5, fifth carbon. So we want the lowest number of carbons, so we should have, it should be 2, 3. Okay, because that's the lowest amount of carbons. That's the shortest way. So second carbon, third carbon. So it should be 2, 3 dash dimethyl, and then our longest chain, which is hexane. So it should be E. Okay. Now the number of hydrogen atoms in decane. Okay, so there's so sure you could draw out for 14, right? The number of hydrogen atoms in decane is, sure you could draw out the molecule and just count all of the hydrogens. But remember that you do have formulas for this stuff. So remember for alkanes, alkynes, remember that it's CnH2n plus 2. Yes, that's your formula for alkanes. So whatever number of carbons you have, for the hydrogens, it'll be twice the number plus 2. For alkenes, it'll be CnH2n, and then for alkynes, it'll be CnH2n minus 2. Okay, so you can kind of see it as positive, neutral, and then negative, right? Here you add 2, here you don't add anything, and then here you take away 2. So alkanes, alkenes, alkynes. Okay, so we have an alkane here. Dec, this little prefix or root word, I should say, tells us how many carbons we have. So we have 10 carbons, and then our hydrogens would just be twice the amount of carbons, so 20 plus 2, so it'll be 22, which would be D. Okay. Oops. Okay. Oh. Let me just move my setup, I guess. All right. Okay. The molecule H2NCH2CONH, or whatever this is, right, contains all these functional groups, except, so this one is tedious, right? But it's not impossible, right? So all we have, what I like to do for these problems is just draw out everything and then see what functional groups we have. It does take a while, I know, but let's see. Let's start here. So we have an N with 2 H's, right? Connected to a carbon that is connected to 2 H's, right? And then this is connected to another carbon that's connected to bonded. Well, I believe it's this. And then H, and this N, CH2, and then it's an O by itself, okay, C, then H2, and then it's a C, HOH, sorry, CH, whoops, and then we have yeah, it's an alcohol, and then CH2, sorry, just trying to make sense of it, I know it's tedious. So we have an OH, H2, And then here, what we have is this OH. Okay, yes. Okay, that should be right. All right, so now all we have to do is just identify all the functional groups. Shouldn't be that hard. This is yes. Hold on. Yes. Okay. Yes. Okay. So all we have to do is just identify all the functional groups. We'll go one by one. Carboxylic acid. Yes, we do have one here. Yes, at the very end, which is this. Okay. So we do have a carboxylic acid. An amine. Yes, we have an amine here. Yes, we do. An amide. Remember, an amide is just an amine double bonded. An amine attached to a C that's double bonded with an O, which is a carbonyl group. So yes, we do have one here, an amide. An ether. Yes, we do have one here. It's this. An alcohol. Yes, we do have an alcohol here. Carbonyl. Sure. I mean, that's not necessarily a functional group. Carbonyl. And then a ketone. Oh, that's the one we don't have. Yes, that's the one we don't have. Yeah, because remember, a ketone is this. CH3. So it's a carbonyl, right? And then this carbon is attached to two carbon chains, right? That's a ketone. And we don't have that here. So I guess the way that you could go about it is to see these dashes, right? And then, how would I explain it? So if you see these dashes, that means that these two are connected. Well, no, that wouldn't make sense. So I guess you have to remember that it's mainly composed of carbon chains, right? Carbon chains. Carbons would like to be attached to other carbons or nitrogens. They wouldn't necessarily be attached to a hydrogen. So whenever you see a dash, that means that it's a carbon and a carbon, or a carbon with a nitrogen. And then whenever you see these group links, that means that everything is attached to everything else, right? It's not bonded per se. I guess that's the best way I could put it. What I mean is, okay, let's look here. H2N. Here. We have an N, right? And then we have the two hydrogens attached to the N. And then this N is going to be bonded, because there's a dash here, with the C. And then this C is going to have two H's bonded to it. But then the C is going to attach to the CO. And remember, we want neutral atoms here. So the reason that the carbon is double bonded to the oxygen here is because this would give it a formal charge of 0. Okay? All right. And the reason that we don't do that here, that there's no double bond here in this oxygen, is because it's an oxygen by itself. If it were grouped with a carbon, then sure, yeah, it would give it a double bond, but it's just an oxygen by itself. Sorry. Okay. So yes, the only one that's missing is a ketone. All right. 16, the number of hydrogens on carbon 4 of 3 hexanon is, so this is simple. We just draw the structure and we just look at carbon 4 and we look at how many hydrogens are there. So let's go ahead and draw 3 hexanon. So first we have to identify our functional group and our longest carbon chain. Here, our functional group would be ketones because it's an on ending, non-ending, right? This N tells us that it's an alkane, right? So it's all going to be single bond. And then this hex, it's going to tell us our longest chain. So it's a 6-carbon chain with all single bonds and a ketone functional group on the 3rd carbon, right? That's what, whenever you have a functional group and you have a number before the name, that means that the functional group is located at this carbon. Okay, so the way that I like to do is just draw the simple alkane of hexane and then just add the functional group in between, well, where it's supposed to be. So hex, longest chain is 6, so 1, 2, 3, 4, 5, 6. Okay. Alkane, that's good. Okay, now a ketone on the 3rd carbon. So we could go either way. So it'll be 1, 2, 3. Okay, so we have a carbon here. So all we have to do really is just do this, or we could do it the other way, right? Because remember, a ketone is just, well, I drew it and I erased it for some reason, but a ketone is just this, right? Okay, so then it'll just be here on the 3rd carbon. So now we have to look at the 4th carbon. So if we counted it 3 from this side, it'll be 1, 2, 3, 4. And let's see how many hydrogens it has. So it'll just be 2. Yeah, it'll just be 2. Because remember, carbon wants to be neutral. Well, it has to be neutral in these cases, right? So we want to form a charge of 0 all the time. Hydrogen provides that one single bond. So then carbon, remember, wants 4, and it has to have 4 in order to have a form of charge of 0. So the hydrogens provide that. So after having a ketone here, right, remember that a ketone is just a carbonyl group with 2 carbon chains by its side. So this is the basic way to do it, right? The reason that we have CH3 here is because we assume that the chains end, but this chain keeps going, right? So it's a carbon here attached to another carbon attached to another carbon. So then it'll just be 2. Okay. Heptanoic acid contains, all right, so we just draw heptanoic acid. Pretty simple, right? We have the heptanoic acid presumably on the 1st carbon because it has no number. We want to look at the last few letters to see, well, the suffix, really. We want to see the suffix to see what functional group we have. Oic acid pertains to carboxylic acid, which looks like this. And then just a carbon chain. Yes, so it's a carbonyl with an OH group. All right. Okay, so heptanoic acid, it has a carboxylic acid, right? The longest chain is 7. This N tells us that it's an alkane. So let's see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Okay, cool. On the 1st carbon here, we have the functional group. So we're just gonna add a carbonyl here and then the OH. And there we go. That's heptanoic acid, right? Okay. So now we just, well, okay, we have to draw it out completely because we want to see the lone pairs. So let's expand this. OH, we would have 2 lone pairs here. Okay. Okay, so remember the reason that we want the two lone pairs is to have a formal charge of 0. Everything has to have a 0 formal charge, right? It's an assumed 0 formal charge for everything. So that's why we add lone pairs. So let's see. No, it doesn't have 2. Okay, let's see here. 4 lone pairs. Yes, that adds up because we have 1, 2, 3, 4. Okay. 7 carbons. That's good. Okay, and 2 oxygen atoms. Yes, that's right. Okay. Let's see its promising. Let's look at D. 4 lone pairs, 6 carbons. No, that's already wrong because it's a hat. So it'll be C. Okay. All right. Let's go ahead and start with the exam 3 review. So we're going to start off with module 8, which is fairly simple. Module 8 says, well, the very first question says, select the correct equilibrium constant expression for the following reaction. Ga2O3 solid plus 3H2 gas in equilibrium with 2Ga solid plus H2O gas. Okay. So remember, our equilibrium constant expression is K is equal to concentration of products over concentration of reactants, right? But we do have a couple of things we have to exclude, right? So we're asked for Kc, and for Kc you can have species in the gas state and also in the aqueous state, right? Because you can have concentrations for those, or you can also find what's it called, pressure, right? But the things that we do exclude are going to be solids and liquids, and that's because, well, you can't really have a concentration of a solid or a concentration of a liquid, right? Also because of another topic in chemistry which we do not cover in this course. So anything that's solid or liquid we have to exclude from our K expression. Okay, so Ga2O3 and Ga have to be excluded because they're both solid. So in reality, we only include water and hydrogen gas. So again, K is equal to products over reactants. So then our K expression would be our products, which is water, and our reactants, which is H2, hydrogen gas, right? And then remember, the coefficients act as exponents. So we're going to have H2O cubed and then H2 cubed. So our correct answer would be E. Okay. For our next question, for 2, it says calculate Kp for the reaction 2NOCl gas in equilibrium with 2NO gas plus Cl2 gas at 400 degrees Celsius if Kc at 400 degrees Celsius for this reaction is 2.1 times 10 to the negative 2. Okay, so we're asked to find Kp given this reaction and given the equilibrium constant, right? Okay, so remember we have to find our equation that relates Kp and Kc. And that equation would be Kp is equal to Kc times our constant, our gas constant, times T, and then the change in moles, right, as our exponent. The change in moles basically means the change in moles here in the reaction. So we're given a Kc, right, so we can plug that in. So I'm just going to put Kp is equal to Kc, 2.1 times 10 to the negative 2, and then times our gas constant, which is 0.0821. Let me just do this. And then our temperature. Our temperature, remember, has to be in Kelvin. So then it's going to be 400 plus 273.15. So 673.15. Okay. Now our change in moles, right? This is pretty simple, right? We just add up all the moles, and whenever you're asked for the moles in a reaction, all that it means really is just the coefficients, right? So remember, this change in moles is moles of products minus moles of reactants, right? Okay. So we just add up the moles. Well, it's the sum of the moles of products minus the sum of the moles of reactants, right? So basically 2 plus 1, well, that's 3, and then minus 2, so it's just 1. So minus 1 is, 3 minus 2 is 1, so this would just be 1, so then whatever value we get here, we just keep it the same because it's to the first power. Okay, so then all we do is just take our temperature times our gas constant, right, times our Kc, which you get 1.16, which is the same thing as 1.2. Cool. All right, let's go to 3. Sorry, okay, there we go. 3 says identify the balanced chemical equation which corresponds to the following equilibrium constant expression. Kp is equal to partial pressure of ammonia over partial pressure of nitrogen gas, 1/2, times partial pressure of hydrogen gas, 3/2. Okay, so then remember Kp and Kc are basically the same thing. It's just that Kp deals with gases, right? Which is pressure of gases. So what I mean by the same thing is that the formula is the same. It's still products, concentration of products, or in this case, pressure of products over pressure of reactants. Okay. So we'll have ammonia as a gas, obviously, because it has a pressure, as our products in equilibrium, right? We know that it's in equilibrium because it has a K expression with, what is it? Oh, yes. With nitrogen gas and hydrogen gas, right? And remember that the exponents are simply just the coefficients of each of these. So we'd have 1/2 nitrogen gas plus 3/2 hydrogen gas. Oh, I know, it's a little sloppy. But yeah, that's basically our formula. So it'll be, it's not A, it's similar. It's E. Okay, cool. Let's do 4. Sorry, my light source is a little failing me a little bit. Okay, 4 says on analysis, an equilibrium mixture for the reaction 2H2S as a gas is in equilibrium with 2 hydrogen gas as a gas plus S2 as a gas was found to contain 2 mole H2S, 3 mole H2, and 1 mole S2 in a 3-liter vessel. Calculate the equilibrium constant for this reaction. Okay, so this one's simple, okay? It just looks very difficult. But you're given moles, you're given your reaction, and then you're given the volume of the vessel. Okay, so we are asked for Kc. Remember that the equation for Kc is just products over reactants, concentration of products over concentration of reactants. And I really want to emphasize concentration, right? Remember that in this course, we use molarity as our concentration, right? Well, not in this course, but in chemistry, we use molarity as concentration. And remember, molarity is moles over liters. So we're given moles and we have the liters. Well, we have the liters of the vessel, which, you know, these moles can occupy. So here we can just put, we can say H2S, H2, and then S2. Right, like I said, molarity is moles over liters. So then H2S is 2/3 molar. H2 would just be 1 molar because of, 3/3. And then S2 would just be 1/3. Okay, these are concentrations. So now we can just plug it into our equation. Remember, it's products over reactants. We have H2 and S2 as products. So H2 has a concentration of 1, and it's squared because it has a coefficient of 2. And then S2 is 1/3, and it has has an exponent of 1 because, well, its coefficient is 1. And then our reactants is just 2H2S, which is 2/3 with an exponent of 2. Okay, so this is gonna get pretty messy, right? But I mean, okay, so 1 squared is just 1. So in reality, this is just 1/3 over 2/3 squared. So we can plug this into our handy dandy calculator. So we can see that's 2/3 squared, 0.44. And then it's 1/3 over that. So 1/3 divided by 0.444, 0.75, which should be D. Yeah, cool beans. All right. And then number 5. It says, consider the following reactions and their associated equilibrium constants. Thus, for the reaction A plus 2B is an equilibrium with D plus E, having equilibrium constant Kc. So it's asking us, using these two, how do we get to this? Right? That's what it's asking us, right? So, okay. So let's write the Kc for this. So it's products over reactants. So it's concentration of D times concentration of E over concentration of A times concentration of B squared. Right, this is for this reaction. What this question is saying is, using these two, how do we get here? That's all it's saying. So then K1 is going to be C over A times B squared, and then K2 would be C, and then over C over D times E. Okay, so basically using these constants, these equilibrium expressions, how do we get to here? And here you're using, here it's asked, well, okay, so the multiple choice answers are basically giving you mathematical methods of how to get there, right? So yes, you could go through all of these, but I mean, I'll just go ahead and say you have to use B, K1 over K2. And the reason for it is because you want AB squared at the bottom, right? We want it here. And then we want DE at the top, right? Using simple algebraic methods, whenever you divide a fraction by a fraction, you have to do KFC, right? Keep, flip, change. So let's do that. So K1 is C over AB squared, and then K2 is CDE, right? So remember, whenever you divide fractions, it's basically like multiply. So remember, it's keep. You flip the sign from division to multiplication, and then you change this, right? You make the inverse of it. So it'll be DE over C. Right, so then we multiply across, so it's CDE over AB squared C. And our C's would cancel out, so then we'd be left over with DE over AB. So this is basically just to see your math skills, basically, right? There's no real formula, and yes, all of these methods could be valid, right? You could have to, you would have to multiply K1 or K2, or have K2 at the top and have K1 at the bottom. It really just depends on the question, right? But you really have to put your math skills to the test. So we got there, right? We wanted DE at the top as a numerator and AB squared as our denominator, and we got there. So then our answer is B. Okay. So now let's go over to module 9. Well, no, just kidding. This is still module 8. I guess, yeah, they flipped these around. Oh no, this is still module 8. Module 9 is acid and base chemistry. This is still module 8, I think. Okay, anyways, that's fine. So 6 says, for the following reaction at equilibrium, which choice gives you a change that will shift the position of the equilibrium to favor the formation of more products? So we want the reaction to shift to the right. That's what we want. So remember, you have to remember the Chatelier's principle, right? Whenever you have a reaction at equilibrium, if you ever make a change to the reaction, the system will try to compensate in a way, right? To make sure that the system stays in equilibrium. Here, we have 2NO-Br as a gas in equilibrium with 2NO as a gas plus Br2 as a gas, right? And we're given delta H of the reaction. So it's positive, so we know that this is endothermic. One thing to remember is that going from reactants to products is an exothermic reaction, and going from products to reactants is endothermic. This has to do with the creation and breaking of bonds, right? So there's this thing that happens that when you go from products and create, when you go from reactants and create products, right, you're creating bonds, which in return releases energy into the system, which is a loss of energy, which means that there's heat involved, right? On the flip side, when you're going from products to reactants, you're breaking bonds, so then the species will kind of keep their energy, right? So the creation of bonds releases energy. The breaking of bonds makes the species keep their energy. Okay, so this is an endothermic reaction. So we're going from products to reactants. So the reaction kind of favors this way, right? So we want it to favor the products more. So how do we kind of tilt this reaction in order to make it go this way? Well, since the reaction is already going to the left, this way, to the left. I don't know why I did that with my hand. It's already going to the left, right? In order to favor more reactants, we kind of have to take away one product, right? If you think about it like a scale, it's an equilibrium, and it favors this side more, but we want it to go this side. We want the system to compensate this side. So if we take away a product, then the system would kind of favor the products. So let's see which option allows us to take away products. So it'll be B. B, yes. All right. Okay, let's go over 7. At 700 Kelvin, the reaction to SO2 as a gas plus O2 as a gas is in equilibrium with 2SO3 as a gas has the equilibrium constant Kc 4 times 10 to the 6. If the following concentrations are present, is the mixture at equilibrium? If not at equilibrium, in which direction, as the equation is written, left to right or right to left, will the reaction proceed to equilibrium? Okay. So we're given a Kc value, right? But we're already given these values, presumably at equilibrium, right? But we can check if it's at equilibrium. If the values that we get from using these concentrations is equal to Kc. Yes. Because we already have an equilibrium constant, and we can use an equilibrium constant expression to find a Kc using these concentrations. Okay, and if they're the same, then we know that it's at equilibrium. If not, then we have to see which side it favors, the reaction favors, or should favor in order to reach equilibrium. Okay, so again, our equilibrium constant expression is products over reactants. So we have only one product, which is SO3. So it'll be 5 squared over our reactant O2. And then it's SO2, which is 0.020 squared. Okay. So, I mean, this would just be 25. 0.020 squared is 4 times 10 to the negative 4 times 0.010. Whoops. Okay. So just to simplify this, it would just be 25 over 4 times 10 to the negative 6. Okay. And then we can just plug this in. That'll be 1, 2, 3, 4, 5, 6. Okay. So it'll be 6.25 times 10 to the 6. So this is our K value once we used these concentrations, right? So we can see that it's not at equilibrium. 4 times 10 to the 6 and 6.25 times 10 to the 6 are obviously not equal. So we know that the reaction is not at equilibrium. So then we have to find out, okay, which way would it favor? And well, to answer that question, we have to look at our K expression, right? This value is way higher than this value. We can agree on that, right? So how do we get this value, this larger value, to go down to a smaller value? And I mean, the answer is simple, right? We have to favor more of the reactants. because there are a denominator. Yes. I guess take, for example, well, okay, so if we write fractions, right, 2 over 1 is 2, right? We can see that when the denominator is less and the numerator is more, we get a greater value. But then when it's 1 over 2, we get 0.5. Yes, so if we see that, we can see that our denominator is greater than our numerator, then we'll get a lesser value. So it's the same principle here. Since we have this larger value and we want it to go to a smaller value, we have to favor more our reactants in this case. So the answer is no, right? The reaction is not at equilibrium, and it'll have to shift from left to right to favor the reactants. Sorry, no, right to left. Yes, right to left. Okay. Yes, it should be C. Okay, let's see 8. Identify the conjugate base of HPO4 2 minus in this reaction. Well, this one's pretty simple. It's just looking at where the PO4 went, right? So in this case, well, we have to remember that acids donate and bases accept H protons. So in this case, HPO4 is treated as an acid, and it gives its H proton to HCO3 minus, which in return makes carbonic acid. So this would be our conjugate base. Okay. Let's look at 9. For the reaction at equilibrium, 2SO3 in equilibrium with 2SO2 plus O2, we were given a delta H, 198 kilojoules per mole. If the reaction temperature increases, the equilibrium will. So it's kind of similar to number 6, right? So we're given an endothermic reaction, which means that it's from products to reactants, right? Because it's endothermic. Okay, so then in this case, our reaction will go this way. Okay, so we're already seeing a favor going to the left. So then we ask, if the temperature increases, what would happen to the equilibrium, right? So that if we favor more this side, right, we increase, I guess for you guys to see it better, and it makes more sense. We're going for products to reactants, right? So then the delta H is in the reactant side, plus 2SO3. 2SO2 plus O2. Right, we already have a delta H on this side. So it's saying if we increase the heat, where will the reaction go? Right? So if we already have heat here, the system will try to kind of alleviate the heat by shifting the other way, kind of thinking of this reaction as a balloon, right? So if we increase the heat, on the side that already has the heat will shift to the right as it tries to compensate. Okay. Shift to the right. Okay. Cool beans. New day, at least for me. For the video, it won't really make a difference. But okay, let's continue on with with exam 3 review. We left off on number 10. it says the reaction is 2N2O5 as a gas in equilibrium with 4NO2 as a gas plus O2 as a gas. Suppose a reaction starts with N2O2 is equal to 0.3 molar, NO2 is 0.20 molar, and O2 is 0.20 molar. And then at equilibrium, we get N2O5 with a concentration of 0.10 molar. Calculate all concentrations at equilibrium. We're asked to sketch a reasonable plot to equilibrium for this process and to calculate the equilibrium constant and the numerical value of Q. Okay, so we're given initial concentrations, right? Remember, Q is at any point of the reaction, right? So, and this is Q initial because it has this little knot at the bottom. So with these reactions initially, we can calculate Q right off the top. And even though these are numbered, we don't necessarily have to do these in this order, because first we need to calculate all our concentrations at equilibrium. Okay, and then I can show you all how to calculate the equilibrium constant and Q. Okay, so remember Q is just as K, which is concentration of products over concentration of reactants, with the exponents being the coefficients. So let's just do Q real quick. So it's 0.20, right, because NO2 and O2 are going to be our products. 0.20 has a coefficient of 4. O2 has no coefficient. Okay, and then we have 0.10, the exponent of 2 because of that coefficient. Okay, so then we could just calculate Q. So it's 0.2, okay, times 0.20. All right, so that's 3. I'm just gonna write it down here so I don't lose track of it. Over 0.1 squared. Okay, so that's just 0.01. So it's 3.2 times 10 to the negative 4 divided by 0.01. Okay, so then Q initially will be 0.032. Okay, so that's our Q. That's this one, right? Okay, and then we need to find our equilibrium constant. So we can't really do that until we have our concentrations at equilibrium. So what I'll do, what we have to do actually is just set up a nice table. Okay, so then with this reaction, I'm just gonna put it here. I have to leave space for the plot. So we have this reaction, right? Initially, we have these concentrations, right? Remember that ice is initial, change, and then equilibrium. So for N2O2, for all the species, actually, we have the initial concentrations. So I'm just gonna put these as initial. We don't start off at 0. 20, and then 0.20 again. Okay. Now the change, remember, is just minus the coefficient x. So it'll be x and then coefficient, and then it's either minus or plus, depending if it's a product or reactant. Remember that reactants deplete, so it's going to be negative, and then products are going to form, so it'll be positive 4x and then just plus x here. Okay, and then equilibrium. So then here it'll just be 0.30, right? Our initial concentration minus the change, and then 0.20, and then the change, and then 0.20 and change. Okay. So then here, if we were given a K value, we could easily just solve for X, and then just plug X in, and then that'll give us our concentrations at equilibrium, right? But in this case, we don't really have K. We can't solve for X given the K, right? But we are given this piece of information, which is pretty critical, which is that N2O5 at equilibrium is 0.10 molar. So we're already given our concentration at equilibrium here, right? So then we know that it's 0.10 molar for N2O5, okay? So from here, we could just find our X, because we want to see, okay, 0.30 minus what number multiplied by 2 gives us 0.10, right? And then, we can solve for it mathematically, right? But we know that for 0.30 to be 0.10, it has to be minus 0.2, right? So then we can say that it's just 0.1 times 2 gives us 0.10. Well, it gives us 0.20, which is what we need to get to 0.10, right? So then, we know that our X is just 0.1 molar because of that information. So then we could just apply that everywhere else. So 0.20 plus 4 times 0.1 is just going to be 0.4. So this at equilibrium is 0.60, and then this would just be 0.30 molar. These are all molar. Okay. So we have our concentrations at equilibrium, right, which is what it asked. We have our Q initially, and then at this point we can calculate K. So remember, K is just products over reactants. So our products is our 0.60 to the power of 4 times 0.30 over 0.10 squared. Okay, so while I was recording, I realized that I made a mistake here. Right, I got confused with these two values. Instead of 0.10, here at the bottom, it's 0.30. I apologize. So that'll give us a value of 0.09. Right, so if we do that calculation again, we would get here. We get 3.56 times 10 to the negative 3. That's for our Q. I apologize. Okay, so now here, this is actually correct. It'd just be divided by 0.01. Okay, so then here our K will be 3.89. That's our K value. Okay. So we've already calculated our Q. We have our equilibrium constant. We have all the concentrations at equilibrium. All we have to do is just plot this reaction, right? So then we're just gonna start off with our little graph. Here at the bottom, we're gonna have concentration in molar. No, that goes up here. And then here's just gonna be time. And then at a certain point, the reaction will reach equilibrium. And we already know those concentrations, right? So now we just have to find a way to plot it. So we can see our values don't really exceed a lot. What we could do, right, is just have 1 molar here because no value here goes over 1 molar. So 1 molar here, and then half of this would just be 0.5, and then that'll give us a good kind of visual aid. So a little trick that I like to do, I'm not sure if rulers are allowed on the exam, but what I used to do is just use this. Like I used to use the back cover of my calculator to kind of roughly estimate. Right, it's a rough estimate. Obviously, you don't have to be super precise, but we just want it to make sense. Obviously, you don't want 0.5 here and then 0.25 over here, right? But okay. All right. So we have our starting concentrations. So, okay, let's do half of 0.5. Half of 0.5 would be around almost like here. This is 0.25. Okay. So then 0.30 molar would be around here. 0.20 molar would be around here. And then, well, we have 2.20, so that's actually too far away. Let's say 0.20 is here. Okay, that's 0.20. That's 0.30 here. Okay. So then from 0.30, we go down to 0.10. So half of, say this is half of 0.25 is 0.125. So then 0.10 would be around here. So then we go from 0.30 down to 0.10, right? And then we reach equilibrium, okay? Notice how it's negative, right? One, because we go from a larger number to a smaller number, but also because it's a reactant, which means that it depletes, okay? So now, for the species that are starting at 0.20, we have one that goes up to 0.30. So what we can do is just have it kind of stabilize at 0.30, right? And then we have one that goes up to 0.60. So it's a little bit above 0.5. So we're gonna have a species that does kind of like, that is double the amount of oxygen, okay? Just draw the lines a little thicker. Okay. And it's always important to label. So this is N2O5, and then this is the one that goes to 0.30 will be O2, and then this one is NO2. Okay. All right. Cool. So that's how you would do that problem. Okay. Let's go on to pH, acid-base chemistry. Okay. Let's see. 11 says, what is the H plus ion concentration in a 4.8 times 10 to the negative 2 molar potassium hydroxide solution? Okay, so we're asked for H plus, and we're given a base, right? Remember that H plus is kind of exclusive to acids. So from this compound here, we can't really find H plus, but we can find ways to find H plus, right? So from here, we can find OH concentration, which is not what we're looking for. We can find OH concentration, and from OH we can find POH, and from POH we can find pH, and from pH we can find H plus concentration, right? So it's kind of going back and forth on these things of pH, pOH, but that's kind of how these problems go. Okay, so what we know about potassium hydroxide is that it's a strong base, right? Because it has a group 1 element. So then it would dissociate completely. So this would go on to be potassium ion plus hydroxide ion. And because they dissociate completely, because it's a strong base, both of these would have the same concentration. Okay, so like I said, we have to find a way to relate OH to H+, and that's by finding your pOH first. Okay, this way we can find pH because we know that 14 is equal to pH plus pOH. Okay, that's why we want to find pOH first, because we can relate it to pH, and from pH we can find the H+ ion concentration by just doing base 10 negative pH, right? And that'll give us our H+ concentration. Okay, so pH is just the negative log of your OH concentration, negative log. So our pOH is 1.32. Okay, I'm just gonna 1.32. Okay, now we're gonna do minus 14, right? It would give us a negative number. Oh, sorry. Or let's just do 14 minus 1.32. It's the same thing, it's just positive. So this is pH. Right, pH is equal to 12.68. Okay, and then from pH, we're able to find H+ concentration. So then what we do is we just put this as a negative, and then we just put it to base 10. We get 2.1 times 10 to the negative 13, which is E. Okay, cool. 12, which one of these statements about strong acids is true? All strong acids have H atoms bonded to an electronegative oxygen atoms, two electronegative oxygen atoms. Not all of them, right? Because you have hydrochloric acid, which is strong, and that's the exception. Strong acids are 100% ionized in water. Sure, okay. The conjugate base of a strong acid is itself a strong base. No, that's actually wrong. So if you have a strong acid, it will actually have a weak conjugate base, and vice versa. If you have a strong base, it will have a weak conjugate acid. So that's wrong. Strong acids are very concentrated acids. That's not necessarily true. You can have a very low concentration of a strong acid. Strong acids produce solutions with a higher pH than weak acids. No, that's not true. It depends on your initial concentration. Okay, so our answer is B. All right. 13 says the OH concentration in a 1.0 times 10 to the negative 3 molar barium hydroxide solution is. So it's asking for the OH concentration of a base. So we don't really have to do any back and forth like we did on question 11, right? So all we have to do is just identify barium hydroxide, whether it's weak or strong. So we know that barium hydroxide is a strong base, and strong bases and acids dissociate completely. So then we have Ba2 plus 2 OH minuses, right, to balance out the reaction. Okay. So because they dissociate completely, both of these are going to have the same concentration. But there's something that we have to look at, right? We have to look at the amount of OHs that we have. So yes, both of these would have the same concentration, but we have to take a look at how many OHs we have. We have twice as much OHs, meaning that the OH concentration overall would be twice this initial concentration of the compound. So our answer would be D, because it's twice the amount of concentration. Okay. So let's look at 14. 14 says if pH is equal to 9.33, OH concentration is. Again, this is kind of going like back and forth. So we want to find OH concentrations, and we can't really find that from pH, but we can find that from pOH. So again, we're relating pH to pOH. So remember, it's 14 minus pH would give us our pOH. So we know that pOH is 4.67. Okay. And all we have to do is just put this base 10. Negative pOH would give us our OH concentration. So 4.67 negative to the base 10. Okay, so we get 2.14 times 10 to the negative 5. And what we have to do here is just look at the process that we did, right? So we took pH, we did 14 minus pH, right? And that'll give us pOH, and it's negative. We do negative pOH to base 10 to get our OH concentration. So it would be C, right? B and A are very similar, just that here we have a negative 14 minus 9.33. It's just 14, it's not negative 14. And then here we're missing the negative sign in front of the operation here. So let's see. 15 says if the Ka values of pyridinium, methyl ammonium, hydrogen cyanide, and acetic acid are 5.9 times 10 to the negative 6, 2.3 times 10 to the negative 11, 4.9 times 10 to the negative 10, and 1.81 times 10 to the negative 5 respectively. According to these values, which one of these acids would have the strongest conjugate base? So like I said before, a strong base or acid will produce a weak conjugate of itself, right? So we have to look at these Ka values, right? These Ka values will tell us how strong or weak they are. So the lower they are, the weaker the acid or the base. They're acids. So the smaller the Ka value, the weaker they are. Okay, so then we have to look at the smaller Ka value, and since we know that it's a weak acid, in return it would produce a strong base. Okay, so obviously the smallest one is 2.3 times 10 to the negative 11, which is methyl ammonium. So since it's a small Ka, it means weak acid, thus will produce a strong conjugate base. So it's methyl ammonium. Okay. Now let's look here. Okay. Calculate the pH of the mixture when 200 mils of 0.20 molar sodium hydroxide is mixed with 500 mils of 0.20 molar HOCl and equilibrium is reached. Ka for HOCl is 3.2 times 10 to the negative 8. Shown the net ionic equations for any reactions that take place in the chemical reaction that you are using to perform the pH calculation. Okay, so we're asked to find pH from mixing HOCl and sodium hydroxide. So let's do that reaction real quick. So we have HOCl plus sodium hydroxide. Okay, so we know that this is an acid. HOCl is an acid because it has a Ka. So remember, acids donate. So we would produce actually water. Yes, we will produce water I don't want to put water there. We will produce water, and then it'll be sodium OCl. Okay, it's a double displacement reaction. Okay, so this acid would donate its H proton and the H proton. Well, it's a double displacement, right? So the H proton would go to the OH and the sodium would go to the OCl. So it's NaOCl plus water. Okay. So remember, this is a buffer problem, right? But it's odd. I'll just treat it as a titration problem. So remember, for titration problems, you want to turn whatever you have into moles, right? Basically treating it like a limited reagent problem. So we have 200 mils, which is 0.2 liters, times 0.2 molar. So of sodium hydroxide. So we have 0.04 moles of sodium hydroxide, okay? And then HOCl, we have 500 mils, so that's 0.5 liters times 0.20 molar. So we have 0.1 moles of HOCl. So then we don't know how much is produced here. We don't count water, right? I guess, yeah, we could treat this as 0 moles. 0 moles. And then we want to make a makeshift ice table. Well, no, it will be an ice table because equilibrium is reached, sorry. Okay, so that's initially, the moles initially, and then the change. The change will simply be the limiting reagent, right? The least amount of moles. So it's minus 0.04 moles, and then it'll be minus 0.04 moles here, right? And it's minus 0.04 because it's the limiting reagent, and these are reactants. So remember, they deplete. And then here it'll be plus 0.04 moles. Okay, so at equilibrium, we have 0 sodium hydroxide, so the reaction can't go on any further. And then here we have 0.04 moles of NaOCl. And then here we have, well, it's just 0.06. Oops. 0.1. Yeah, 0.06 moles. Okay. All right. So we have the moles of each. And actually what we have here is a buffer because we have a common ion here. So because we have a common ion, we could just use the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of acid over conjugate base. Okay, so because we have our acid, right, and this would be its conjugate base. Okay, so then let's just do that real quick. So conjugate base is 0.04, and it's all right if you do it in moles. You can also do it in concentration in molar, right? All you have to do is just add up these volumes, and then just turn your moles into molarity, but this works just as well with moles, so that's fine. And then pKa, I'll just write out negative log of 3.2 times 10 to the negative 8. Yeah, it's messy, sorry. Okay, so then 3.2 times 10 to the negative 8. Take the negative log of that, which is, I'll just write it down here, 7.5. We can just round it. And then 0.04 over 0.06. You take the log of that. So we would get negative 0. Let's just say 2. Okay, so then it's 7.5 plus 0.2, negative 0.2, so then our pH would just be 7.3. Oh, can you guys see? Yes, okay, nice. So that's our pH. Okay. Let's go over 17. 17 says for phosphoric acid, Ka1, we're given Ka1, Ka2, Ka3, which of the following represent the conjugate acid-base pairing pertaining to Ka2. Okay, so this one's pretty simple. We just have to look at these reactions, right? Remember, phosphoric acid is H3PO4. Okay, and then we want to see which one is the Ka. The Ka2 for H3PO4. So remember, we have 3 Kas because each one of these pertains to every time there's a dissociation of H ions, right? We have 3 Kas because we have 3 hydrogens that we can give away, right? So then the first Ka is the first dissociation of a hydrogen atom, right? The second Ka is the dissociation of the second hydrogen atom, and then the third Ka would be the dissociation for the third hydrogen atom, right? So what happens here is that phosphoric acid mixed with water yields, so acids donate, in this case water will act as a base, so we would get H2PO4 minus plus hydronium, and this would be our first Ka, right, because it's the first hydrogen that we gave away. So if we keep this pattern up, right, we can see that for Ka2 it would just be H2PO4, right? Even though this is the conjugate base, it still has an H proton to give away, so it's still an acid. So if we put it against water again, we should get HPO4 minus 2 plus hydronium. Okay, and this is our Ka2. So then it should be H2PO4 and HPO4 as our conjugate acid-base pair, which is B. Okay. Over number 19. So 19 says the Ka value for formic acid is 1.75 times 10 to the negative 4 when 451 mils of 0.777 molar formic acid is mixed with 352 mils of 0.150 molar potassium hydroxide, and a neutralization reaction occurs, and the chemical system comes to equilibrium. Write a balanced equation, and then show how you determine pH. Okay. So let's see. So we have formic acid, right, which is a weak acid, plus potassium hydroxide, which is a strong base, right? From this reaction, we will get potassium formate, I believe it's called, and water, right? Okay. So here we can see that we have a buffer because of the common ion effect here, right? Potassium, since it comes from a strong base, it's gonna be just a spectator ion. Okay, so basically this is a titration problem, and we can calculate pH via the Henderson-Hasselbalch equation because we do end up having a buffer. So we are going to treat it as a titration problem, meaning that we have to turn this information into moles. So 451 mils is 0.51 liters times 0.77. Okay, and that's formic acid. So we get 0.35 moles. Okay, and then 352 mils is 0.352 liters times 150. So that's around 0.05 moles. Okay. Now, we don't include water here. We have an ice table, sorry. It's just kind of forced to have it. So then our change is going to be our limiting reagent, which is potassium hydroxide. So we will have none of this, minus this, plus this. We have 0 of this, 0 moles, 0.05. Okay. Cool, so now we have 0.30 moles, and then we have 0 moles of here, and then we have 0.05 moles here. Okay, cool. So now we could just plug in our Henderson-Hasselbalch. pKa plus log of acid, and then conjugate base. Okay. So now our acid is going to be 0.30, right, because of formic acid, and then our conjugate base is 0.05 moles. Take the log of this, and then pKa. pKa is just the negative log of Ka. That's around 3.75. Okay. So now we just do 0.05 divided by 0.30, the log of that, plus 3.75, which is 2.97, which we can round to a pH of 3. Okay, cool beans. And then finally, for this exam review, we're gonna go over 20. It says a 150 ml solution of nitrous acid, Ka 4.5 times 10 to the negative 4 is titrated with a solution of 2 molar potassium hydroxide. The equivalence point is reached when 86 ml of the base has been added. Determine the pH of the solution during the titration when 43 ml of base has been added. Okay, so here, yes, we can do the titration, the moles and everything, right? And we will more than likely end up with a buffer solution, right? But the thing that we have to look for is this basic keyword, which is equivalence point, right? And at equivalence point, we have to remember that pH is equal to pKa. So if we wanted to find the pH, right, we just have to find our pKa, which is 4.5 times 10 to the negative 4. So then it's around 3.35 pH. So that kind of gets rid of our headache.